morning, Margaret.
What? Anyway, work for me, work for you all. But I like to pace, so I'm going to pace. Welcome to the third day and to this program. You are now all indoctrinated in a very large scheme, Ponzi or trickle down or some other thing. We worry about the name later. But always, always, always remember that once you are a part of anything Repro, you are always part of anything Repro. When the year ends, that doesn't end your association and your relationship to this group and all the other sister, aunt, and uncle and relative groups from the other programs. But hopefully we'll try to also commingle, some cross-fertilization amongst those groups too, because the community who have been through some sort of Repro training, it's actually quite large and quite extensive. And this program is really cool. ReproNIM itself, kind of lives in the neuroimaging world. This is really great opportunity to get, yes, some neuroimaging here, but also to get beyond that to other things that we don't directly do, but the trickle down is very important there. So welcome to the fellowship of the Repro. The great thing about speaking now is you've heard already virtually everything I'm going to say from other people. So my task is really pretty simple, just to come back and remind you of a couple things that you've already heard and to put a slight extra color commentary onto some of the things you've already heard. The goal from the reproducibility principles point of view is pretty simple. There's only 5 things you need to do. That is plan everything, version control everything, use standards for everything, annotate everything, and share everything. Piece of cake, and you've sort of heard dribbled through the presentations already, some of the tools and elements and rationale for these various things. Even though I said it sounds simple, just 5 things, each of those things though can be fairly daunting. So the other most important thing is you don't have to do it all at once. These are all sort of aspirational types of things. Each objective has easier things you can do and harder things you can do. Maybe GitHub is hard for a little bit for some people, but version controlling, you can do version controlling through other ways. GitHub is very important, but it's important to do some sort of version tracking and work your way up to potentially more challenging types of things. So amongst our goals is to help identify the easier pieces of these things, so you can get a little bit more reproducible each time you do a new study and work your way up. You don't have to get there all at once. Don't get daunted or overwhelmed by all the things that get buried into that overview. But each of these things will come to bite you in the future. And bite all of us, who, when you don't plan, when you don't track the versions of things, when you don't use standards, and when you don't annotate. And a lot of this, as we've said, is also about the future you. It's one thing to do it for you now. It's another thing to do it for the future you. I used to be embarrassed with this sort of subtext to what ReproNIM is. Our slogan was, we take easy things and make them hard. I've come to embrace that a little bit. The things that have been easy for bad reasons, and they lure us into continuing to do some not optimal types of things. Now, when I say bad practices, I'm old and I've been doing bad practices since before they were even invented. So that's and the goal is to get better. But by just doing what the lad before you has done, we propagate things that have trickled down, and we don't take the opportunity to introspect and improve our approaches. So when we take the easy route, it feels easy sometimes, but it's also causing problems for the community and probably causing problems for your future self. So we need to embrace delayed gratification, and this has come up before, and this is your future self type of thing. Spending some time now that may make today's task a little bit harder, a little bit more time consuming, will be valuable for the future you, even if it's for yourself. That's valuable time you'll save later. So always remember, that work now is not wasted. It's work you probably would have had to do anyway. We may just be playing around with the temporal ordering of things. Think about a pre-registration of a paper you're going to do. It feels like a hassle to write the pre-registration before you collect the data or go grab the data. It's a waste of time. Why am I doing this pre-registration? Well, practically speaking, that pre-registration is writing your method section now. All that work you do, to write that, to do the power calculations, to plan the analyses, are all things you're going to write in that methods section of the paper you're going to write. So it's not a waste of time to do it now. It's just the little temporal reordering of the order you used to do things in. So we search for ways to take the things that look like more work or harder now and remind ourselves that they are not really a waste of time and there is benefit to them. And the other concern, of course, is that familiarity breeds comfort and content. And again, we're used to doing the things we used to do. And again, to try to push ourselves to be aware of what the challenges are and how to try to do a little bit better with each new thing that we do. I'm not going to spend much time on the reproducibility problem origin. You've heard a lot about that already, but I do, in my particular application area, which tends to be mental health applications in kids or adults using neuroimaging techniques. This is a statement from Tom Insel, the head of the National Institute of Mental Health, back in 2012 or so, where he was lamenting that the progress in improving anything. After at that time 30 years of neuroimaging studies and 30 years of genetics studies, yet the kid in your psychiatrist's office with autism, the kid with drug addiction, your grandparents with Alzheimer's or Parkinson's disease, the outcomes are pretty much the same today after 30 years of genetics and imaging as they were 30 years ago. So there's been a huge investment in imaging and genetics, but the practical outcome of that in terms of the patients who nominally we're working for has been very little. But if you think about that, there's been billions of dollars invested in that. Great. There's no grant has ever gotten this money and hasn't come up with some finding and published something. So there's gobs of publications. But what this generates, and again, it has to do with these power and false positive types of things that have come up. Is there's a profusion of statistically significant but minimally differentiating biological findings that have permeated the literature, and so these are findings that can sometimes be approximately replicated. You can hand wave about things that do and don't application, but they're done in a way that can really not be neither confirmed nor refuted in a sort of progressive, useful way. So trying to make sure that we get out of this sort of conundrum of just doing these things, publishing things, filling the literature, getting grants, filling the literature, getting tenure, filling literature, getting your next grant, and yet our patients, the people we're doing this for, need to get something instead of us just getting published and tenure and things like that. So anyway, so we're trying to push this culture and use that, and the reasons that mental health has had issues. It's some of the same issues that we've talked about here: low power, but also the target disorders are very problematic in mental health. We often talk about, I'm going to do a study of autism. Well, autism isn't one thing. Most things become mental health topics because they're spectrum-y types of things. Schizophrenia is not one thing. Parkinson's disease is not one thing. All these things, get lumped into that title, but it's a disservice to treat them all as one thing. And so better targeting of what it is, the things we're looking at, in our case, in the brain, actually affect in terms of the patients, has kind of been mismatched over the years. And things like RDoC, research domains of classification and things like that, are trying to get around some of the traditional challenges of just looking at disease labels and what findings we have with them. So, oops. Why is that here? Okay. I'm not going to show this video for you. How many have seen the making a peanut butter and jelly sandwich video? Okay, good number. You're great. These slides will be made available. I highly recommend watching that. Like many funny videos, it is so funny and sad at the same time. I'm also not going to show it here. Marianne Martone, I think, has one of the lectures in here on the FAIR data. She uses one of my favorite videos in that lecture, the data sharing snafu in 3 acts. Anyone from that title remember seeing that video?
It's a cartoon.
It's a cartoon, old school, done a long time ago, but one of these animations that are generated from the text. It is, again, so funny and so sad. Even this one's sad, and when you think about peanut butter jelly having some relationship to your science, the data sharing snafu is really a bit sad when you think about data and things like that. But anyway, the point here is the concern about the prior sentence being approximate replications of findings in a way that can neither confirm nor refute. So that's one of the things we're trying to overcome, is to do science in a way that can be confirmed or refuted. And the premise here is it's impossible to confirm or refute something that you first cannot replicate. The other conjecture here is traditionally we do not publish articles in a way that really encompasses the entire complexity of the thing that we're trying to describe. So when it comes to doing these very complex studies, there's so much that we do that every element, every choice we make can make a difference in what that outcome is. And because everything we do can make a difference in that outcome, we have to somehow document everything that we do in our act of our doing sort of scientific work. So exact instructions are hard, which is why you need to watch that video. One of the first things that surprised me is something like the observation that even the operating system of your computer, matters. You can go back through most of the literature and ask, in this paper, what operating system did they use for the software, the statistics they used, or the image processing they used? Almost never recorded the operating system. Maybe the software is named, maybe the version of the software is named, but what operating system? That just seemed like a detail that no one would care about. Well, it turns out if you do some studies, and JB's group has done a lot of this kind of work, the exact same version of the same software running under different operating systems, under different architectures, can generate different results. That's not a problem in the sense that one or the other isn't right or wrong. It's only an issue that needs to be recorded so that if someone's trying to replicate or redo what you've done, that's just a detail that needs to be known. Clearly, the amount of data matters. And this is a silly little example of looking at some particular volumetric observation. I guess it's a sex effect on hippocampal volume. Back in 2005 or so, there was a few hundred cases available in the public domain. You look at a particular question and you see big error bars, you cross zero, there's no statistically significant difference between male and female hippocampal volume in kids. Well, later on, more data becomes available. You look at the same question and things change. That's not surprising, but it just reminds us that how much data you have, how big the underlying effect size is, how stable your measurements are all sort of embedded in every observation we made. So things that aren't significant now might be because they're not significant, or might be just that, it's evolving over time and we need more data. So again, always data size matters. We often think of our tools as very precise and do the things that they say they do. If I want to go out and measure the volume of a brain structure, I could run off and use FreeSurfer. I love that tool. It was developed by folks in my neighborhood at the time. It was based on some of the data that we generated that went into the trials for that. So my favorite anatomic tool. Great, doing volumes, that's what I use. Well, there's other tools, ANTS, for example, or FSL. Other tools can make volumetric observations of the same structures. Are they the same? When I say volume of the caudate, does it matter if I've used FreeSurfer or FSL or ANTS? Yes, it does. And even though nominally these are tools that measure the volume of a structure may actually depend on which tool you're using to do it. And the more complex the structure, the more complex the measurement, curvature or thickness or other features, get more and more fuzzy. There's more and more differences in how different tools can approach these questions that, again, I'm not going to say anything about who's right or who's wrong, but the correlation between a FreeSurfer volumetric measure and a FSL and a ANTS volumetric measure is kind of problematic. They correlate darn well. P to the minus 1,000, FreeSurfer and ANTS correlate. But correlation and giving a similar result are not the same thing. And clearly, the slope between those two representations are quite different. And so there's all sorts of examples where same data, different tools, different answer. The volume of a structure is not the volume of the structure, it's the volume of the structure as represented by some particular tool or tool version, run on some particular system, run with some number of subjects. Also alluded to before, exactly what statistic you use matters. This is all obvious, but sometimes we don't remember how important all these decisions are. So my point here is just to make sure we're all on that same page and all just have these in the back of our head. This again is a silly little toy example. Again, looking at the sex effect of the hippocampal volume in ping data, the pediatric imaging, neuroimaging and genetics study, 1,200 subjects, age 3 to 21 or so. So it's a big N, 1,200 or so. So it's a large study. Looking at the volumes, FreeSurfer volumes, great. But there are many covariates we know about that. In ping, we know the age of the subject. We know we're searching for sex. We know the total brain volume. We know the socioeconomic status. We know, which site is the multi-site study. We know a genetic ancestry factor feature. So what do you use in your model to look at the sex effect? Well, historically, we got a covariate for brain volume, and some studies will say SES matters, clearly site matters. So again, exactly of all the covariates you could throw into that study, you often pick and choose some. Sometimes you start with a bunch, you see almost a significant effect, then you say, geez, I'm using so many covariates. I could just drop one of these covariates. SES is not making an impact on this. Even though I know SES can affect this, it's not in my data. So let me just not use that covariate. So we can come up with ways, kind of a type of key hacking that can mix and match what we actually do. In this little example, there's 128 different models I could do with that set of covariates. The models that don't have brain volume show a fairly large effect. But we know the covariate for brain volume because there's a large sex effect in brain volume itself. So fine, ignore those models. And also these don't actually explain much of the variance of the data. The R squared, are only, 0.2. So we're only explaining 20% or so of that variance in that metric. So fine, forget it. We better use brain volume. So here's the models with brain volume, explaining a lot more of the variance, great. But depending on exactly which permutation of age, site, SES, total brain volume, and genetic ancestry factor, we can get fairly different predictive values and coefficient for sex, some of which are significant, some of which aren't. Big study, what you report depends on what you happen to use there, and you could see that effect either appear or not appear based on what model you use. Again, I'm going to say nothing about what the right model is. I'm going to say you must declare and describe and even explore model selection, and that there's a price to pay statistically for more variables, but the brain is a complex thing, so do it, report it, and treat that appropriately. So anyway, everything matters. Report everything. You've already seen this graph probably twice, if I remember correctly. My take-home point from this is because of the fact, so we don't see published data that is not significant. It's kind of one of the take-home points from here. And that's a illustration of the file drawer effect, the fact that you don't publish things that aren't significant, and that leads into this publication bias, that the things that get published tend to be the things that are significant. So my next step from this particular graph is to then reconsider things like meta-analyses and the impact of that graph on your meta-analyses. When you go, so I'm going to take an example here in autism, looking at the corpus callosum volume. It is a observation that for 20 years you can go back through the literature, find 17 different articles that report something about the corpus callosum in autism. You can do a meta-analysis of that data, and you can see a very clear 0.5 effect, standardized effect size of the effect of corpus callosum volume. Great. 17 different articles in the literature, very clear meta-analytic result. Gosh darn it, the corpus callosum must be smaller in kids with autism. Each of those are fairly small studies. Many of those studies reported a significant difference, but only a small majority of those studies reported a significant difference themselves. But the meta-analysis of that, since a lot of them are in that same direction, reports a fairly clear observation. It turns out, after bigger publicly available databases of autism data become available, you easily find publicly available data and want to ask yourself, gee, that meta-analysis from those small studies reported something very clear. If that was true, it should be a no-brainer to take some publicly available data, bigger data set now, make that same observation and repeat that in a new mega-analysis as opposed to the old meta-analysis. Well, a meta-analysis. So meta-analysis is you take published things from the literature and sort of look at the consistency of both. A mega-analysis is just take raw data and redo the study from scratch. So instead of 17 publications with their particular observation, I take the 1,000 subjects and do a direct analysis of that with a large data set as opposed to the individual little data set. Yes. Again, this should be a no-brainer. If we trusted the literature, if the literature and the meta-analysis procedures do what they're supposed to do, I should be able to take this abide the autism brain data exchange data, measure volumes with FreeSurfer, whatever tool you want, and you can identify site effects. Yay, if you see them. You can identify age effects. Yay, no problem. You can identify the sex effects you expect. Yes, no problem. But problem that the diagnostic effect is not significant. Now, wait a minute. This was a no-brainer. This was supposed to be, clearly, a diagnosis effect on the corpus callosum volume. But yet the mega-analysis does not confirm that. In pondering, that this study, because it had 1,000 and some subject, 600 and almost 700 subjects, it was very well powered, to find this effect. Whereas all of the meta-analytic studies that went in, each, maybe had the best power was maybe 30.3, was the building blocks, from this. So combining publication bias, only things that are significant get published, that literature, and that missing bit of of the unsignificant findings. It turns out that that is false positives and things like that are sort of driving that observation. Now, one of the take-home points here, it's not that the corpus callosum is not doing something in autism. The corpus callosum is also mediated by things like total brain volume. Total brain volume and autism have some associations. Things like the corpus callosum are mediated by IQ. Well, IQ and the diagnosis interact. So in the end, the initial pointer that something's going on in the corpus callosum wasn't wrong. It's just that that was not the direct effect. And you need to do, actually, if you want to disentangle what's going on, is a much more intricate play between IQ, total brain volume, and that diagnostic factor, at least, is going on there, so that to disentangle that. So again, the things that come out of the literature in certain types of situations, especially where that missing data, in this types of sort of volumetric meta-analyses, can be misleading about what we really know. So just a grain of salt and to keep in mind. Also going to give you one of my takes on a type of figure you've seen 2 or 3 times already, and this is great. There's a variant of this, though, that these words, you've heard it here a bunch of times, and it's what kind of the literature and the world thinks, to put reproducible, replicable, robust, and generalizable. I define these slightly different, and I apologize that if I add any confusion to this by defining things a little bit differently. I want to highlight some of the features of this plot, same content, same ideas, but I approach it slightly differently. Thing one is you do a study. You have some data, you have an analytic approach, you do that. To me, the basic, that first upper left corner on that other plot that they call reproducible. The term I like to use here is re-executable, in that reproducible to me just has too many other connotations to it. What I think is a clearer term is re-executable. If someone can take that exact same data and that exact same approach and get that exact same answer, call it reproducible if you want, but I would call that re-executable. And that's a basic feature that we're sort of striving for our publications to be re-executable. Why? Because do I want to re-execute your study? No, but I do want to look at these other boxes. I want to look at the generalizability. I want to see what happens if I mess around with the data. Take out some data, put in some data, swap the data. A type of generalizability. How generalizable relative to the data is this particular observation? So I need to play with the data piece, keeping everything else the same. We're scientists, we know how to do controlled experiments. But unless I can start from what I did in my paper, I can't mess around with the data, or you can't mess around with the data unless you're starting from that same place. Similarly, I need to make my data available so that if you say, oh, geez, you used FreeSurfer, gosh, damn it, and you should have used ants, I want to mess around with the processing part of that. But unless you can start from the same data or start from the same place I started from, we don't know how to interpret the differences you might get if you mess around with other alternatives about how that approach is done. So I sort of put both of these dimensions into generalizability, either playing with the data under controlled situations or playing with the method under controlled situations. We strive for this, sort of what they did call generalization. Whoops, sorry, wrong way. What they did call generalizability over here, which is what we want. If a finding that we have is about autism and is about the corpus callosum or whatever, we want that to be about the corpus callosum measured anyway, about autism diagnosed anyway, if that's what the real conclusion is. So again, we're striving to get to where similar data, similar analysis yields a similar result in order to have a finding that we have some trust in its generalizability. Most of what we do is not super generalizable. And that's okay. Often what we do is make inferences and comments about things that are often a little bit of a stretch. When I do a study in autism, even if I had 1,000 subjects, it's very hard for my conclusion to really be about autism. It's probably about the particular features of the types of kids with autism who ended up in my study, which may not be generalizable to autism. And because it could be a fairly heterogeneous types of subgroups and subtypes that take a different mix of those, you may get a different answer. So again, getting more precise in terms of how to create our conclusions is also important to try to make conclusions that stand up to generalizability. Okay, so all of this was introduction to the cornerstone of reproducible research is transparency. I'm going to work our way up to this. Transparency is annotating and sharing with others through some sort of publication or sharing precisely what operations were performed and on what data in a fashion that could be re-executed by someone in an attempt to replicate, ultimately generalize that finding. So again, the exact tools that each of us will use in this objective, will change, but that's kind of what I'm trying to instill in all of us to think a little bit more and to work, incrementally more in trying to come to that kind of observation. So what does that mean to our publications? We've got to throw out the current publications and create a new type of publication that's really rescued. Well, no. Even within our archaic and mostly broken publication systems of the currently, we can achieve these increased re-executability in what we publish by, of course, writing the words. We do need humans to read this. We do need humans to understand what and why we're doing. But in addition to the words, we need to make some way in that publication to link to or be associated with the data that went into that. We need to make some way to identify and to make available the workflow specification that went into that analysis. We need to make available and somehow accessible to others the actual execution environment that was used. And then we need to make those results available. The data may not be able to be available to everyone, but gosh darn it, someone other than the original author needs to be ethically authorized to be able to access that, and be able to participate in this type of thing. So publications with things like link outs and references can accomplish, even in traditional publications, connections to all of these elements. And so there's a number of examples of publications that have a connection to the data that goes into them, have a connection to the GitHub repo for the workflow specification, have connections to a Docker or Singularity or some sort of containerized environment that can re-execute the exact configuration of the computational system, and the results can be shared as well. So each of these elements can be woven into the current publication scheme. The other important thing about this, though, is traditionally in the old days, we thought of a scientific publication as a finding about a disorder or something, where the publication is really about that finding. Caudate is big in this population, or corpus callosum is small in this other population. And that's kind of what was put on the pedestal, this biological, clinical finding. Everything else was just kind of either ignored, or even if you do what I'm advocating here, becomes a sort of second-class citizen. But our first-class citizen tends to be that biological observation. Corpus callosum, smaller, kids with autism. The culture we kind of need to evolve a little bit, again, trying to get you all to buy into and help support, is that all of the work you did to come to that conclusion is actually equally important and equally first class things that we as scientists do. That data, particularly, may be the most important thing that you do. You can come up with some false positive ridden claim about corpus callosums and autism, but the data you used, these 127 kids with autism, the MRI scans and things like that, that can persist much more valuably and maybe more true of what it is over time than your conclusion that you made. And yet we tend to second-class citizenize our data. And then even when you do data share, it's kind of, oh, look at me, I'm data sharing for the good of society. But no, I'd actually like you to share your data for the good of yourself. I'd like you to publish that and get another publication. So ultimately, yes, you could have your fragile biological conclusion, but you should also have your less fragile, more citable, more reusable data citation that will probably ultimately most likely have a bigger impact than the false, except for all of our data, which is and our conclusions are right, but many of them are tend to by accident not be right. So get the data publication, turn what would have been one publication into 2 elements on your CV. There are many ways to publish and get full peer review credit for publishing data, and the citation on data and the citation on papers that include data is demonstrably higher. So again, this is all even in the traditional academic sense, ultimately good for you. So again, yes, maybe you had to take some time to publish that data. On the other hand, that time that you might have taken there is actually beneficial for you. So just keep that in mind. Similarly, if you come up with a cool workflow, again, people publish software all the time, that's great. But even when you design a workflow for a software analysis, that is a publishable entity. There are peer review ways. They may not be super high impact of themselves, but there are ways to document, publish, get a DOI for your analysis approach or an analysis container that you make available and reusable to others. Citable, includable in your CV, and probably more reusable and cited by others than the conclusion that you come up with. Or maybe you're lucky and a lot of people cite your conclusions. If that's the case, they're probably also going to want to use your data, cite the methods that go with that. So again, the opportunity for 3 times impact, 3 more, 3 publications out of what traditionally would have been 1 if publication count and citation count is the measure we're stuck with. There are ways to work within the system to try to take advantage of that. The ramification of doing these types of approaches can be surprisingly impactful. I show an old school PDF, copy of a figure of corpus callosum area and whole brain volume from some paper done a long time ago. That is a static thing, published in a PDF, and fine, they report what the correlation values are and the statistics of that correlation, and they report that, fine. But when we strive to get to this sort of re-executable, fully annotated vision of the world, we then begin to get to these things like shiny plots, things that are living, where you can actually play with certain features of the analysis, change the correlation, change the model that you use and things like that. But in the sort of fully annotated sense, every point on that graph knows an awful lot about it. You can pick a point there. That point, yes, comes from some Excel file somewhere that says, okay, this is subject 17. It's a free surfer run, and then the volume of the corpus callosum is whatever it is. Fine, that's a row in your Excel, your data file. But if that's fully annotated, it knows that subject 17 has some demographics to it. So that point knows who the subject is. That subject knows all of their demographics. So in sort of this linked annotated data world, you can navigate from an observation to the information about the subject, This is a free surfer run, so it used a T1 weighted scan. Well, here's where that T1 weighted scan is. That point is connected via this graph to where that scan is. That scan is associated with metadata. That metadata of the scan knows, what the site it was on, what the TRs and TEs and the scanner manufacturer was. So ultimately, through this annotation, through the linked data types of concept, every point there has, access, to all the other features that relate to that in a much more dynamic and living and reusable and reinterpretable way than the static, PDF, graph, that you might show. And similarly, if I know if that point has an annotation to it that says what workflow was used, well, then you can find that workflow. You can get to the container that ran that workflow and rerun that if you want, or use that workflow to add new data to that particular representation. So again, in the sort of extreme of annotating everything and publishing everything, we generate these sort of connected graphs of all the information about each point that we put there that can then facilitate adding, subtracting, changing, the details in a controlled sort of scientific way, as opposed to otherwise, okay, I'll get some more data. I'll do the analysis a little bit different. I might get a similar answer. I might get a dissimilar answer. If it's dissimilar, I just write a paper saying, I saw something else. It's different. Oh, we use slightly different, and just say, oh, we did some different things, and sort of ignore, why things are different. And every time we find something that is different, we shouldn't just ignore that. There's a reason that if I take another pile of subjects with autism and do a similar analysis and get a different answer, right now I just go off and publish this other answer. Now the literature has two different answers about the same question. We very rarely go back and look at why did I get a different answer in a situation where nominally I might have expected the same answer. Is it to do with the subject? Well, gee, maybe we should understand what it is about the subjects, that is different. Is it because I did a slightly different analysis? Well, gee, we should understand, if that's the source, why that's the case. And we ignore that all the time. And that doesn't make necessarily for high impact science, but it is necessary for us to understand the gosh darn science that we're doing. How am I doing for time? The Ioannidis paper has come up a bunch. Why most published research findings are false. Embedded in that publication is a handful of corollaries that I find fascinating. Many of them are traditional statistical power types of things, studies, when the small studies, small effect sizes, greater number of multiple comparisons, all sort of traditional, problems that runs into in statistical things. Other corollaries that I think are important to remember there is the greater flexibility in design, which drives more measures, is going to inflate your false positive rate. So the more flexibility I could, if I'm doing free surfer and I have 1,000 measures, there's huge flexibility in what I can interpret. I might just go off and look at all those things because I have them. The second I get into that more flexibility about how to analyze the data, the more room for inflation and selecting of the tests I actually do, search them all, and then hypothesize the ones that look most interesting. Harking, hypothesis after results are known type of thing. Also remember that being wrong is not actually a problem. It's probably true that most of our published findings are false, and that's okay. Being false, being wrong is not a problem. Being wrong and not admitting what the potential issues are, is a problem. And being wrong and keeping your observations and things in a little private silo is the problem. False positives happen. False positives are overcome by sharing data. So if you share the data and pool the data, the chance that your false positive finding can be resolved in the future comes from your ability to share the method and sharing the data, so that in the future, a larger, better powered study can evolve from what you've done. So false positives are not a problem unless they're done, hidden and in the dark. all of this needs to be out in the light so that they can fall, not just be single points in the bibliome of observations. One of the other things here is the greater the financial or other interests are, the higher the chance of the research, the less likely a finding is to be true. When gobs of money get thrown at something, there's so much pressure, maybe not to do things illegally or wrong, but man, there's a lot bigger financial incentives. The government watching you, investors, watching you. The chance of something surreptitiously coming through, increases. The hotter a scientific field is, sort of a corollary of that, the hotter the topic is, the more pressure, investigators are under to get into that, cool, hot topic. Creeping in of, false positives and creeps in there. So anyway, so those are kind of fun additional corollaries in this observation. And we just have to be better about our sharing data, multiple teams. It's okay to look at things multiple ways. Ultimately, things are evolving to, as I sort of foreshadowed, one segmentation tool may not be give you the same answer. So there's no reason not to run all of them and look for consensus answers as opposed to one tool versus another. So again, there's various things to do. And the p-value is an evil thing. I'll let the statistical people talk more about that. But p-values are evil. Doing truly reproducible research is hard, but there are many things you can do. And again, over the course of this course, you will learn about things that will help you for that. Again, my point here was to, one, remind you that some of these things are hard, but two, to remind us there are baby steps, small things that we can do to improve the outcomes, and larger steps that we can aspire to over the course. Many educational resources, this course being one of them. And again, as I foreshadowed, you are part of a huge team in this effort. There's other R25 training courses like the ABCD Repronim course, which focuses on the adolescent brain cognitive development data. Also the HBCD, the Healthy Brain, whatever that stands for. And the Repronim training fellows themselves and the Repronim team are all at your disposal. So take advantage of that. And again, this curriculum covers a lot of that, and you have a direct line to all of that. So take advantage of that. So embrace your data and methods, treat them all with due respect, and publish them. And they are all first-class part of your work. Get credit for all of the work that you do. The earlier you plan, the easier things will be. And that's not wasted time. It is just replaced on the timeline of things that you do. Use standards, explore generalizability. Don't just ignore things that are different. And remember, continuous education. You are all part of this lifelong learners mission. So thank you for doing this, and thank you for improving, every day, little bit, along these lines, because it's important for the patients and for the outcomes that we're after. You must do it, though. I'm trying to be nice and letting you think that, thinking about reproducibility is good. But there is an or else to this. Our funding agencies are getting a little pickier and pickier on reproducibility and robustness. So without embracing this, you might begin to have some challenges in funding. The data sharing policy, often your annual reports, you won't get a next year's funding unless you do some of this data sharing mandates. Publications are getting a little bit more teeth in the data sharing and the methods sharing and the reproducibility aspects. So if you don't get published unless you begin to address some of these things, without funding and publishing, you're not going to get tenure. So again, all of these are sort of trickle down of why you need to embrace this. In your spare time, you should watch the John Oliver, This Week with John Oliver 30-minute diatribe on reproducibility in science. Any of you seen that? Yeah, it's great. And again, another one of these videos that just makes you laugh. And there's a link to that here. But in the words of Yaroslav Halchenko, who is one of our data execution experts at Repronym, it was really taking this concept of reproducibility not as an afterthought, but reproducible by design again. So keep that in mind and good luck. And